Hello and welcome to my AE1601 glider project final video. So first, I'd like to take a look at the requirements that were given to us for this project. So my main requirement was I wanted to produce a stable and efficient glider. According to the A1601 rules and guidelines, this meant that I had to reach a 20-foot minimum distance. I wanted an ideal distance of over 50 feet and fit within a 16 by 16 inch platform. However, in order to achieve the 20-foot goal, the 50-foot goal, I wanted to also maximize both dimensions. As we'll go into, there are several aerodynamic and control-related benefits that are derived from this. So, to begin with, looking at the alternative generations and the certain ideas I had, I'd like to begin with wing shape. So, for aircraft, there are three primary types of wings that I wanted to look at: straight wings, tapered wings, and elliptical wings. Straight wings are easy and quick to manufacture, and it's very easy to do center of lift calculations to try and predict a good center of mass point to initially test. Tapered wings provide less drag at transonic speeds. However, all of these advantages were not quite as good as the advantage provided by elliptical wings, where a minimal wingtip vortex drag is observed. So second, I'd like to look at dihedral. So for most aircraft, there are three potential options that we can look at. Dihedral, where the wings point upwards; no wing angle, which is a straight wing, where the wings go directly outward; and enhedral, where the wings point downwards. Straight wings provide neutral stability, and enhedral provides roll instability. However, a active dihedral provides roll stability, which is required to have a glider which is capable of flying in a straight line, even when thrown in a side slip. So for tail configurations, I looked at four different tail configurations. To begin, I looked at a flying wing. A flying wing eliminates extra drag, which is generated by a traditional horizontal tailplane. However, it's difficult to balance an aircraft with a flying wing. I looked at V-tails, which still produce less drag than traditional tails, as there is a vertical stabilizer missing. However, it is difficult to trim a aircraft which is designed this way. I looked at a vehicle with a traditional tail, which is more draggy than any other option, but it's very easy to make and trim. And for the T-tail, unfortunately, it's very similar to a traditional tail. It is simply more difficult to manufacture. So so in the end, I decided to look at three main concepts: an aircraft with a T-tail and a straight wing, an elliptical wing with no dihedral and a normal tail, an elliptical wing with dihedral and a normal tail. Ultimately, I decided to begin by pursuing the elliptical wing dihedral normal tail design. This is because I would be able to have minimal wingtip vortices, I'd have roll stability, and I'd have a simple to manufacture tail that is very easy to control and modify in order to get optimal flight characteristics. So to size my aircraft, I decided to maximize every single dimension. A maximum wingspan allows for a very high aspect ratio with the same amount of lift, which means I minimize my drag due to wingtip vortices. In addition, long wings and a long fuselage allow for the longest lever arms, which means that you achieve the best dynamic stability, which means that in the end, when the glider is thrown, it is able to obtain its level attitude and then maintain that throughout the glide most easily. So as I mentioned, the initial concept was an elliptical platform with a 15-degree dihedral and a standard tail. The elliptical platform it minimized wingtip vortices. The dihedral allowed for roll stability, and a standard tail minimized construction. So here are my calculations. I decided to use the recommended method using the glider's weight, and by finding average velocities, I found that the coefficient of lift was about 0.1, and the total coefficient of drag was equal to 0.0009. As just mentioned, this glider is supposed to fit within a 16 by 16 inch box. Whenever measured, my glider came out to 15.9 inches in length from nose to tail and 15.9 inches from wingtip to wingtip. When I began testing, I decided to construct a cardboard test model. It was exactly identical to my full-scale conception of my regular glider. In order to place the center mass initially, I decided to place it at about third chord. This is a commonly known RC rule of thumb with no specific particular known source. So I decided to shift the center of mass by taping writing utensils to the nose of the cardboard glider. In addition, after the initial test run, I decided to add a 2-degree nose-up trim based off of a rough estimate. and ultimately I decided to shift the center of mass to about 0.7 inches from the leading edge of the wing, which is approximately a fifth of the length of the cord. As I mentioned, cardboard glider testing, the airfoils were kept in the exact same shape and size. However, in addition to shifting the center of mass using ballast, I decided to actually physically shift the wing back 1 inch um, as compared to the cardboard model. So here's a video. It, took it took only a few seconds. However, the glider flew in this peaked shape, reaching an overall distance of about 60 feet. It tolerated a slight side slip, which proved the correctability of the large dihedral. This flight profile is likely a result of tail heaviness or an incorrectly set horizontal stabilizer, which resulted in a stall. As you can see, the initial concept is mostly preserved for the final version. So in conclusion, I'm very proud to say that my glider won its competition. It reached a maximum distance of about 100 feet. The aircraft is dynamically stable and was able to resist being thrown downwards and in side slips, and ultimately stabilize itself and fly straight. It was slightly tail heavy and trimmed incorrectly, so ideally, a future glider would involve a more adjustable horizontal stabilizer. Here are my sources. Thank you very much for watching, and have a good summer.